Polymers in the structure of aircraft. The first successful aeroplane flight was by the Wright brothers in 1903, which lasted 59 seconds and covered a total distance of 852 feet. Since this point, the aviation industry has worked hard to increase the flight time and efficiency of planes in order to maximize the number of flights available and minimize costs. Beginning in the 1920s, the materials making up aircraft have been dominated by aluminium, titanium, and steel. But, as demands for fuel efficiency increase, these metals, which have previously been viewed as lightweight, are now too heavy to be solely relied upon. It was estimated by MIT a few years ago that for every passenger to carry a mobile phone on a Southwest Airlines flight, it costs the company an extra $2.1 million in fuel costs every year. Imagine the difference in efficiency and costs if the overall weight of the plane could be 10 times lighter. Enter polymers. First introduced into planes in World War II as a replacement for rubber components, these are now used in all parts of planes, with over 50% of recent aircraft being built from carbon-reinforced polymers. Of the polymers used in aircraft today, there are two main types: thermosets and thermoplastics. Although being similar in name, these are quite different in nature. Thermosets, which are currently used in most parts of planes, are polymers which are subjected to an initial heat treatment with a catalyst when molded, and are then set in their chemical and physical properties, so are no longer affected by heat exposure. The change is irreversible. By contrast, thermoplastics are those which, when heated, soften and become more fluid. No chemical bonding takes place, and the process is 100% reversible. This means that a thermoplastic can be remolded and recycled without damaging its properties. Polymers hold the upper hand on metals with more than just weight. Certain types of both thermoplastics and thermosets have inherent flame resistance and even flame retardancy. This massively reduces the need for flame retardant additives. In addition, thermosets can survive in extreme temperatures. Notably, polyimide, also known as PI, can work effectively from below 123 Kelvin to 560 Kelvin, and even up to 755 Kelvin for brief periods of time. Add resistance to high wear and friction, and you'll find that PI will last for impressively long periods of time in hostile temperatures. Then comes chemical resistance. Both types of polymers have very high chemical resistance in environments where metals will just dissolve. Polyphenol sulfide, also known as PPS, is a thermoplastic which particularly excels in this area. Finally, there is corrosion resistance. In typical aluminium and steel-based aircraft, one of the largest reasons for structural failure is corrosion between different materials, also known as galvanic corrosion. Thermoplastics in particular can be welded together using resistance welding, by using a wire mesh clamped between the two desired parts and passing a current through it. The parts of the material which are clamped together next to the mesh heat and soften and can be molded together. This allows for pieces to be joined without the need for rivets, thus eliminating corrosion between parts and without damaging the structural integrity of the part. This makes the overall aircraft safer for longer. Thermosets are the more widely used of these two types of polymers. They have been used structurally in planes for over 40 years and have lots of testing behind them. They're the safety net of the aviation industry. Thermoplastics, on the other hand, are much newer to many applications in the aviation industry, despite being widely used elsewhere. Airbus has used thermoplastics on the leading edges of its aircraft for a few decades. However, these are not massively important parts of the aircraft. The Gulfstream G650 is the first commercial aircraft to use thermoplastics for critical control surfaces, specifically the elevator and the tail rudder. Without these, the aircraft would be out of control. These surfaces are made from a carbon fiber PPS composite. PPS is an interesting choice for this, as it has a glass transition temperature, or TG, of 90 degrees C. On hot days and near an engine exhaust, as the elevators are, this temperature could be exceeded. So why does it work? PPS is a semi-crystalline polymer. This means that it can still keep quite a lot of its strength and stiffness above its Tg, while when thermosets go above their Tg, they decompose. PPS, in fact, has been used by the automotive industry at temperatures over 140 degrees for years. There are some good advantages to using thermoplastics over thermosets. They have an almost indefinite shelf life, unlike thermosets, the components of which have to be used relatively quickly after being synthesized. They can also be recycled, and parts which aren't quite up to specifications can be melted down and moulded again. By contrast, if a thermoset plastic is not up to spec, it would have to be thrown out. Parts which have been used for years and need to be replaced can be melted down and used for less important roles. Thermoplastics in their production are also cheaper than those of thermosets, because although the raw material can be more expensive, by finish it can be 20 to 40% cheaper because of reduced handling, processing and assembly costs, due to not needing to be put in an autoclave. An autoclave being basically a giant, very hot oven. Thermosets do have the advantage over thermoplastics at high temperatures, but for the most part, and with more and more research going into them, thermoplastics are on the rise. Who knows, there might even be a plane built entirely out of thermoplastic composites in the future.